Looking up at the night sky and wondering about those millions of pinpricks of light is something humans have been doing for as long as we've existed. From ancient stargazers who wondered about the twinkling lights in the night sky, to modern scientists probing the depths of space with advanced technology, understanding the cosmos and searching for extraterrestrial life represents one of humanity's greatest adventures. This fascination is rooted in the profound curiosity we have about our place in the stars and the desire to answer one of the oldest questions: are we alone? As our technology allows us to peer further and deeper into the cosmos, the possibility of discovering life, whether microbial or intelligent, holds the potential to not only reshape our understanding of the universe, but also redefine our very sense of self and our role in the grand stage we call existence. The origins of life on Earth. The story of life on Earth is one of the most profound mysteries in science. For billions of years, our planet was a hostile, barren rock, covered in oceans and shaped by volcanic activity. But at some point, deep in this ancient world, something remarkable happened. Life began. Today, scientists continue to study this turning point, searching for clues about how simple chemicals could have sparked the processes that would eventually lead to every living thing we see today. When considering the origin of life, the first question we must ask ourselves is, where exactly did it begin? There are a few leading ideas, each offering a different perspective on the conditions that might have allowed the first simple organisms to take shape. Some scientists point to the deep oceans, where hydrothermal vents, essentially cracks in the sea floor that release heat and chemicals from the Earth's interior, could have created the perfect environment for the first life forms. These vents, called black smokers, are rich in minerals and gases, such as hydrogen and sulfur. Around these environments, even today, life thrives in conditions that would seem extreme to us. This has led many to speculate that early life might have emerged in such a place, sheltered from the harsh conditions on the surface of the young Earth. Others think that life could have started in shallow ponds or pools. In these environments, simple organic molecules like amino acids and sugars could have formed naturally, driven by energy from sunlight. Over time, as the water in these pools evaporated and refilled, the concentration of these molecules might have increased, allowing them to interact in more complex ways. This theory, often referred to as the primordial soup hypothesis, suggests that the first building blocks of life might have spontaneously come together, eventually forming molecules that could reproduce themselves. Figuring out how these basic components became life as we know it is one of the most challenging aspects of this mystery. Life, at its simplest level, requires a few things: the ability to maintain itself, to grow, and to reproduce. To accomplish this, even the most basic forms of life need molecules that can store information, like DNA or RNA, structures that can carry out functions, like proteins, and a way to separate themselves from their surroundings, like a membrane. But how could all these components come together? Perhaps the answer lies in the idea of chemical evolution. Over millions of years, the simple molecules that formed on early Earth could have undergone countless chemical reactions, slowly becoming more complex. Some of these reactions might have resulted in molecules that could copy themselves, a crucial step toward life as we understand it. Complex proteins work as catalysts of a great number of biological processes all around us today. But we know that some exceptionally simple molecules called ribozymes have the ability to catalyze or speed up certain chemical reactions. Replication could be one such chemical reaction, and once molecules could replicate, they would also be subject to natural selection, the process that drives evolution. The molecules that could replicate more efficiently or were more stable would slowly become more common. These stable molecules could interact with one another to gradually form more complex systems. Recent research has suggested that RNA, a molecule closely related to DNA, could have been one of the first molecules capable of storing information and catalyzing chemical reactions. The previously mentioned ribozyme molecules are in fact made up entirely of RNA. This is known as the RNA world hypothesis. RNA is unique in that it can both store genetic information and perform functions like proteins, making it a prime candidate for an early form of life. Over time, these RNA-based systems might have evolved into more complex forms of life, eventually giving rise to the DNA and protein-based life that dominates today. But even with these clues, scientists are still left wondering about the spark that initiated life. Some researchers have suggested that the early Earth was bombarded by comets and asteroids carrying organic molecules from space. This idea, known as panspermia, posits that the building blocks of life might have been delivered to Earth from elsewhere in the universe. If true, this theory could mean that the origins of life on Earth were part of a much larger cosmic story, one that could have implications for finding life beyond our planet. Looking at the origins of life on Earth is not just about understanding our own history. It also helps scientists in the search for life elsewhere in the universe. By studying how life might have begun here, we gain insights into how we might find it elsewhere. For instance, we now know that life can survive in extreme environments, such as deep sea vents, frozen glaciers, and acidic lakes. This has expanded our understanding of the kinds of conditions that might support life, even in places that seem inhospitable at first glance. Take, for example, the moons of Jupiter and Saturn. Europa, one of Jupiter's moons, has an icy surface, but beneath it lies a vast ocean of liquid water. Could life exist there, perhaps around hydrothermal vents like those on Earth's ocean floor? Similarly, Saturn's moon Enceladus also has a subsurface ocean, and recent observations have shown plumes of water vapor erupting from its surface. These environments, although far from Earth, might offer the right ingredients for life to form. Even Mars, with its cold, dry surface, was once a very different planet. Billions of years ago, Mars had liquid water on its surface, and possibly a thicker atmosphere. Although Mars is now mostly barren, it's possible that life could have existed there in the past, or might even survive today in some of the planet's underground reservoirs. The study of life's beginnings on Earth is like assembling a vast puzzle with pieces scattered across time and space. Each discovery brings us closer to understanding not just where we came from, but also where life might be hiding in the universe. Whether life began in the deep oceans or shallow ponds, whether it was sparked by chemical reactions or delivered from space, one thing is certain: life is resilient, adaptive, and capable of surviving in environments far beyond our imagination. Defining life. What does it mean to be alive? When we think about life, we tend to picture plants, animals, and microbes, things that grow, move, and reproduce. But when scientists try to define what it means to be alive, things get more complicated. At first glance, it might seem obvious. Life involves things that eat, breathe, and respond to their surroundings. But what about viruses, which don't do most of these things on their own, yet still infect and replicate within host organisms? Or what about robots or artificial intelligence? Can they ever be considered alive if they start to think and act in ways that seem human-like? The question of what defines life has challenged scientists for centuries, and the answer is still not clear. There are a few obvious key characteristics that scientists use as a guide to determine whether something is alive. For one, all living things are made up of cells, which are the basic units of life. Life can be as simple as a single-celled bacteria or as complex as the trillions of cells in a human being. Living organisms also need to grow and develop, usually by taking in energy from their environment. For example, plants absorb sunlight and carbon from the atmosphere to create food, while animals eat plants or other animals to get energy. Another important factor is reproduction. Living things have the ability to make copies of themselves, either by producing offspring or through dividing themselves into multiple copies, ensuring that their species can continue to exist. Finally, life responds to the environment around it. Whether it's plants bending towards sunlight or animals fleeing from danger, This interaction with the surroundings is a critical part of being alive. But what happens when we find something that meets some of these criteria, but not all? Viruses are a good example. A virus can't grow or reproduce on its own. It needs to infect a living host to make more copies of itself. For this reason, many scientists don't consider viruses to be fully alive. However, viruses do evolve, and they can adapt to their environment, much like living organisms. This grey area makes it difficult to come up with a perfect definition of life. Even if we agree on a working definition of life, there's another big question to consider. Would life elsewhere in the universe follow the same rules? As we continue to search for signs of life beyond Earth, scientists have to question their assumptions and hypothesize about how different alien life might be from the forms of life we know. Life on Earth is carbon-based, meaning that carbon is the backbone of the molecules that make up living organisms. Carbon is unique in that it can form a wide variety of complex molecules, which are necessary for the diversity of life. This makes carbon the ideal foundation for building the proteins, carbohydrates, and fats that are essential to life as we know it. But could life exist based on something other than carbon? Some scientists believe it's possible. Silicon, for example, is a close relative of carbon on the periodic table and shares many similar chemical properties. Silicon can form complex molecules, and it's relatively abundant in the universe. This has led to speculation that silicon-based life could exist on other planets, especially in environments that are different from Earth. However, there are challenges with this idea. Silicon-based molecules tend to be less stable than carbon-based ones, especially in the presence of water. Since water is so important for life on Earth, some scientists remain skeptical about the possibility of silicon-based life in environments where liquid water exists. And speaking of that magic liquid, water plays one of the most crucial roles in sustaining life on Earth. It is often called the universal solvent because it can dissolve a wide variety of substances, making it essential for the millions of chemical reactions that take place inside living cells. Water also has some unique properties. It remains liquid over a wide range of temperatures, and it's excellent at storing and transferring heat. This allows life on Earth to survive in a variety of climates, from freezing polar regions to scorching deserts. Because of its importance to life here, scientists believe that water would likely be essential for life on other planets as well. Still, the search for alien life has led some researchers to consider the possibility that life could exist in environments that are drastically different from Earth's. For example, some moons in our solar system, like Titan, have lakes and rivers made of liquid methane instead of water. Methane exists as a liquid at much colder temperatures than water, and if life were to exist in such an environment, it would have to operate at much lower energy levels than life on Earth. Could there be organisms out there that use methane the way we use water? It's a fascinating idea, and scientists are only just beginning to study what such life forms might look like and how they might function. With our current scientific understanding, the question of whether life can exist without carbon or water remains an open one. While carbon and water are ideal for the type of life we're familiar with, that doesn't mean they're the only options. It's possible that somewhere in the universe, there are life forms made of entirely different materials, living in environments we can hardly imagine. In their attempts to define life, scientists have come up with a list of criteria that must be met for something to be considered alive. But as we've seen, these criteria are not always clear-cut and may not apply universally. Life, as we know it, follows certain rules based on the chemistry of carbon and water. However, when we look to the stars and wonder whether life exists elsewhere, we have to keep an open mind. It's possible that life on other planets could be based on different elements, different chemistries, and different rules. The search for life beyond Earth is not just about finding creatures that look like us or follow the same biological patterns. It's about expanding our understanding of what life is and what it can be. The search for habitable zones, where life could thrive. Despite all that speculation, Ultimately, the most practical way to discover alien life is to search for the kind of life we have on Earth. After all, that is the only life we know for sure can exist in this universe. As we continue our search for life beyond Earth, one of the main concepts scientists focus on is the idea of a habitable zone. This is a region around a star where conditions might be just right for life to thrive, especially life as we understand it. The habitable zone, or the Goldilocks zone, is where a planet is neither too hot nor too cold for liquid water to exist. Since water is essential for life on Earth, finding planets within these zones increases the chances that life could develop. The distance between a planet and its star is the key factor in determining whether it's in the habitable zone. If a planet is too close to its star, the heat would cause any water on the surface to evaporate, creating a dry and inhospitable environment. On the other hand, if a planet is too far from its star, the water would freeze, making it difficult for life to survive. Earth is located in the Sun's habitable zone, which is why our planet has been able to maintain liquid water for billions of years, providing the foundation for life to flourish. The idea of a habitable zone isn't limited to stars like our Sun. Stars come in different sizes and temperatures, and this affects where their habitable zones are located. For instance, larger and hotter stars have habitable zones that are much further away from the star. Smaller and cooler stars like red dwarfs have habitable zones that are much closer. In fact, many planets orbiting red dwarfs are currently the subject of intense study because they may offer some of the best chances of finding life outside our solar system. Now, one example of a planet that has captured the attention of scientists is Proxima Centauri b, which orbits the closest star to our Sun, Proxima Centauri. This star, which lies about 4.2 light-years away from us, is a red dwarf, meaning its habitable zone is much closer than that of our Sun. Proxima Centauri b lies within that zone, raising the possibility that it could have liquid water and perhaps even some form of life. However, there are challenges. Red dwarf stars are known for producing powerful solar flares, which could strip away a planet's atmosphere and make life difficult to sustain. Currently, scientists have been unable to determine if Proxima Centauri b even has an atmosphere. Figuring out if that atmosphere could support life would be an even further challenge that scientists would need to crack. Ultimately, however, a planet's atmosphere is an absolutely key factor in determining whether it is truly hospitable to life. Even if a planet is located in the habitable zone, it needs to have the right kind of atmosphere to regulate temperatures and protect any potential life from harmful radiation. Earth's atmosphere, for example, plays a crucial role in maintaining the temperatures that allow water to remain liquid, while also shielding us from the Sun's more dangerous rays. Without an atmosphere, a planet could experience extreme temperature swings, making life difficult to survive. Mars, for instance, is in the outer edge of the Sun's habitable zone, but its thin atmosphere means that any water that once existed on its surface has mostly disappeared. In the search for planets in habitable zones, scientists use telescopes both on Earth and in space to detect distant worlds. One of the most important tools for this search has been the Kepler Space Telescope, which has discovered thousands of exoplanets, planets that orbit stars outside our solar system. Many of these exoplanets are located in the habitable zones of their stars, giving scientists a long list of candidates to study in more detail. Some of these planets are close to the size of Earth, raising hopes that they could have similar conditions to our blue marble. However, just being in the habitable zone doesn't guarantee that life exists. Conditions on the planet itself, such as its composition, atmosphere, and geological activity, all play a role in determining whether life can thrive. Earth, for example, has plate tectonics, a process that helps regulate the planet's climate and recycle essential elements. Without this activity, it's possible that Earth's atmosphere and climate might not have remained stable enough to support life for billions of years. When scientists search for habitable planets, they look for clues that these processes might be happening elsewhere as well. Some moons in our solar system also present intriguing alternative ways for life to survive. Even though they don't lie within the habitable zone of the Sun, Jupiter's moon Europa and Saturn's moon Enceladus are both icy worlds that appear to have liquid oceans beneath their frozen surfaces. These moons are far from the Sun, but they are heated by the gravitational forces exerted by their parent planets, creating an environment where water can remain liquid. In these cases, the energy needed to sustain life comes not from the Sun, but from the internal heat generated by tidal forces. Scientists are particularly excited about Europa and Enceladus because their subsurface oceans could be similar to the deep sea environments on Earth, where life thrives around hydrothermal vents. So, while the habitable zone concept is a helpful guide, it's not the only factor to consider. Life might exist in places that we haven't even thought to look yet, in environments that are very different from what we're familiar with. As technology advances, scientists are developing new ways to study these distant worlds in greater detail. One of the most exciting developments is the upcoming launch of more powerful space telescopes, like the James Webb Space Telescope, which will be able to analyze the atmospheres of exoplanets. By studying the gases present in a planet's atmosphere, scientists can look for signs of life, such as oxygen or methane, which are often associated with biological activity. The idea of a habitable zone has given scientists a roadmap for where to look, but it also challenges us to think beyond the familiar and to consider the many ways life might adapt to survive in a variety of environments across the cosmos, discovering new worlds beyond our solar system. Of course, making richer and richer discoveries requires investment in the tools and techniques astronomers use to uncover the secrets of our universe. Discovering exoplanets truly opened up a new chapter in humanity's quest to find life elsewhere in the universe. And it is hard to believe that it was only recently that we found direct proof that planets existed outside of our solar system. For centuries, we only knew of the planets orbiting our own sun. The idea of planets around other stars was purely theoretical. That changed in 1992 when astronomers found the first confirmed exoplanet orbiting a pulsar, which is a rotating neutron star that is highly magnetized. Since then, thousands of exoplanets have been discovered, each one giving us new clues about how planetary systems form and how diverse they can be. One of the most common methods astronomers have used to detect these distant worlds is called the transit method. This technique involves monitoring the light from a star and watching for tiny dips in brightness that occur when a planet passes, or transits, in front of the star. As the planet moves between its star and us, it blocks a small portion of the star's light, causing a slight dimming that can be detected by telescopes. By observing how often these dips in light occur, scientists can calculate the planet's orbit and determine how far it is from its star. The size of the planet can also be estimated based on how much light it blocks. The transit method has been incredibly successful, especially with the help of space telescopes like Kepler, which was launched in 2009 to search for Earth-like planets. Kepler observed over 500,000 stars and discovered nearly 3,000 exoplanets using this method, including planets located in the habitable zones of their stars, with conditions potentially suitable for life. By studying the light from these transits, scientists can even learn about the atmosphere of some exoplanets, looking for signs of water vapor, carbon dioxide, or other gases that could indicate the presence of life. Another important technique for finding exoplanets is the radial velocity method, also known as the Doppler method. This technique doesn't rely on seeing the planet directly. Instead, it measures the effect a planet has on its parent star. As a planet orbits a star, its gravity pulls on the star, causing the star to move slightly in a small circle or wobble. This wobbling motion changes the wavelength of the star's light in a way that can be detected by telescopes. When the star moves toward us, its light is compressed and shifts toward the blue end of the spectrum. When it moves away, the light shifts toward the red end. By measuring these shifts, astronomers can determine the planet's mass and the shape of its orbit. This radial velocity method was used to discover the first exoplanet orbiting a Sun-like star, 51 Pegasi b, in 1995. This planet was a surprise to scientists because it was a gas giant, like Jupiter, but it orbited very close to its star, completing an orbit in just 4 days. This type of planet, known as a hot Jupiter, was unlike anything seen in our solar system and forced astronomers to rethink their models of how planetary systems form. Since then, the radial velocity method has been used to find many more exoplanets, particularly those that are larger and closer to their stars, where the gravitational tug is stronger and easier to detect. Both the transit and radial velocity methods have their strengths and limitations. The transit method is better at finding planets that pass directly in front of their stars from our viewpoint, but it can miss planets that have orbits that don't align with our line of sight. On the other hand, the radial velocity method can detect planets regardless of their orientation, but tends to be more sensitive to larger planets that exert a stronger gravitational pull on their stars. By combining both methods, astronomers can gather a more complete picture of an exoplanet's properties. As technology has improved, astronomers have developed even more ways to discover and study exoplanets. One such method is direct imaging, where powerful telescopes take pictures of planets by blocking out the light from the star, allowing the much dimmer planet to be seen. This method is extremely difficult because stars are so much brighter than the planets that orbit them. However, in recent years, advances in telescope technology have made this a reality, and scientists have directly imaged a few exoplanets, particularly those that are far from their stars. One other method is gravitational microlensing, which takes advantage of the fact that massive objects like stars and planets can bend light due to their gravitational pull. When a distant star passes behind a closer star with a planet, the gravity of the nearer star acts like a lens, magnifying the light of the distant star. If there is a planet orbiting the closer star, its gravitational pull will create a small, additional magnification, which can be detected by astronomers. This method is particularly useful for finding planets that are far from their stars, including planets that may be floating freely in space, unbound to any star. Each of these techniques have added to our understanding of the incredible diversity of exoplanets. Some exoplanets are gas giants like Jupiter and Saturn, but many others are rocky, like Earth and Mars. There are also planets called super-Earths, which are larger than Earth but smaller than Neptune. Some planets orbit very close to their stars, completing an orbit in just a few days, while others have long elliptical orbits that take them far from their stars for most of their year. Particular attention has been paid to planets with rocky surfaces and the potential for liquid water for the ultimate goal of finding an Earth-like planet where life could exist. Goldilocks. Planets. The hunt for Earth-like worlds. Since our best bet for discovering life is finding planets analogous to our own, it is worth taking a closer look at some of the ones we've discovered so far. Planets where conditions might be just right for life are often called Goldilocks planets, a term inspired by the fairy tale where Goldilocks finds a bowl of porridge that is not too hot and not too cold, but just right. Similarly, a Goldilocks planet is one that is located in the habitable zone of its star, where temperatures allow liquid water to exist. Water, as we know, is essential for life, making the presence of liquid water one of the key factors in identifying potentially habitable worlds. For a planet to be considered just right for life, it must meet several conditions. The distance from its star is the most obvious. Too close, and the planet will be scorched, its water boiling away into space. Too far, and any water on its surface will freeze into ice. Earth, with its moderate climate, sits comfortably in the middle of this range, allowing water to remain in liquid form for billions of years. This has created an environment where life has not only emerged, but thrived. Rocky planets, like Earth, are more likely to have solid surfaces where liquid water can pool. Gas giants, like Jupiter, might have thick atmospheres with clouds of gas, but they lack the solid surfaces needed to support life as we know it. Super-Earths, which are planets larger than Earth but smaller than Neptune, could be ideal candidates for life if they are rocky and have atmospheres that can support liquid water. The discovery of other Goldilocks planets was one of the most exciting developments in modern astronomy. With the help of space telescopes like the Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, or TESS, scientists have found a growing number of these planets orbiting other stars. One of the most famous Goldilocks planets is Kepler 452b, discovered by the Kepler Space Telescope. This planet orbits a star that is similar to our Sun and lies within its star's habitable zone. Kepler 452b is about 60% larger than Earth, making it what scientists call a super-Earth. It's likely a rocky planet, and its distance from its star suggests that it could have temperatures that allow water to stay liquid. This makes it a prime candidate for further study, although given that it is located about 1,400 light-years away from us, direct observations are extremely challenging with current technology. Closer to home, the TRAPPIST-1 system has also captured the attention of scientists. This system contains 7 Earth-sized planets orbiting a cool, red dwarf star. Of these 7, potentially 4 are located in the habitable zone, where conditions might be right for liquid water to exist. The TRAPPIST-1 system is relatively close to Earth, at a distance of just 40 light-years, which makes it an excellent target for future observations. Because the planets are so close to their star, they complete their orbits in just a few days, making it easier for astronomers to study them using the transit method. These planets are tidally locked, meaning one side always faces the star while the other side remains in darkness, which could result in extreme temperature differences across their surfaces. However, if they have atmospheres that can distribute heat, life could potentially survive in regions where temperatures are more moderate. While the discovery of planets like Kepler 452b and those in the TRAPPIST-1 system is exciting, finding Goldilocks planets is just the first step. The next challenge is determining whether these planets truly have the conditions to support life. One of the key factors is the presence of an atmosphere. A thick atmosphere can help regulate a planet's temperature, protecting it from the extreme heat of its star or the cold of space. Earth's atmosphere is made up of nitrogen, oxygen, and small amounts of other gases, including carbon dioxide, which traps heat and keeps the planet warm enough to support life. If a planet has too much carbon dioxide, however, it could experience a runaway greenhouse effect, similar to what happened on Venus. Despite being located near the inner edge of the Sun's habitable zone, Venus is a hostile world, with surface temperatures hot enough to melt lead. Its thick atmosphere, composed mainly of carbon dioxide, traps heat, creating an extreme greenhouse effect. This shows that even if a planet is in the habitable zone, the composition of its atmosphere can dramatically affect its ability to support life. On the other hand, if a planet has too little atmosphere, like Mars, it might not be able to retain heat or liquid water. Mars is in the outer part of the Sun's habitable zone, and there's evidence that it once had rivers, lakes, and maybe even oceans of liquid water. But today, Mars has a thin atmosphere, and most of its water is locked away in ice, with only traces of liquid water found near the surface. Without a strong atmosphere to protect it, Mars has lost much of its water to space, and the planet's surface is cold and barren. Understanding the atmospheres of Goldilocks planets is crucial for determining their potential habitability. Next-generation space telescopes like the James Webb Space Telescope will allow scientists to study the atmospheres of exoplanets in unprecedented detail. By analyzing the light that passes through a planet's atmosphere during a transit, scientists can determine the chemical makeup of the atmosphere and look for gases like oxygen, methane, and water vapor, which could signal the existence of life. But the search for Goldilocks planets should not distract us from considering how life might adapt to different conditions. While liquid water is essential for life on Earth, it's possible that life elsewhere could thrive in environments that we would consider extreme. For example, Some microbes on Earth, known as extremophiles, can survive in boiling hot springs, freezing polar ice, or the crushing depths of the ocean. This raises the possibility that life could exist on planets that are not in the traditional habitable zone, as long as they have some source of liquid, energy, and protection from harmful radiation. Exomoons and life. Can moons be habitable? While the search for life has largely focused on planets, moons around large planets known as exomoons could easily also offer environments suitable for life. In our own solar system, moons like Europa and Enceladus have become prime targets in the search for extraterrestrial life, despite being far from the Sun's habitable zone. These moons suggest that life could thrive in unexpected places, not just on planets in the traditional sense. As scientists look at moons around distant exoplanets, the possibility of habitable exomoons opens up another avenue in the search for life beyond Earth. The prime example of Europa, one of Jupiter's largest moons, has fascinated scientists for decades. Beneath its icy surface, there is strong evidence of a global ocean, kept warm by tidal forces generated by the gravitational pull of Jupiter. This process, called tidal heating, occurs because Europa's orbit is slightly elliptical. As it moves closer to and then farther away from Jupiter, the moon's shape is constantly stretched and compressed. This creates friction and heat within Europa's interior, which prevents the ocean from freezing solid. The presence of liquid water under the ice is one of the key reasons scientists are so intrigued by Europa. Water is essential for life, and Europa's subsurface ocean could harbor conditions similar to those found in Earth's deep-sea environments, where life thrives around hydrothermal vents. These hydrothermal vents on Earth's ocean floor release heat and minerals from the planet's interior, creating a rich environment where bacteria and other organisms live without sunlight, relying instead on chemical energy. If similar vents exist on Europa's ocean floor, they could provide the necessary ingredients for life. Missions like the upcoming Europa Clipper, set to be launched on the 10th of October 2024, aim to study Europa's surface and search for signs of these vents or other indicators of habitability. By flying close to Europa and analyzing its icy crust and the water plumes that erupt from its surface, scientists hope to learn more about the moon's potential for life. Similarly, Enceladus, a smaller moon of Saturn, has also captured people's attention as a possible home for life. Like Europa, Enceladus is covered in ice, with evidence of a liquid ocean beneath its surface. In 2005, the Cassini spacecraft made a remarkable discovery: geysers of water vapor and ice particles erupting from cracks near Enceladus's south pole. These plumes shoot into space from an underground ocean, offering scientists a direct glimpse into the moon's hidden environment. Chemical analysis of the plumes revealed the presence of organic molecules, salts, and other compounds that are essential for life. The discovery of these plumes has led to speculation that hydrothermal activity may be occurring beneath Enceladus's ice, similar to what is found on Earth. The heat generated by Saturn's gravitational forces could be driving this activity, making Enceladus one of the most promising places to search for life in our solar system. Future missions to Enceladus could probe deeper into these plumes, looking for more complex organic molecules or even microbial life. Both of these examples raise an important question. If moons like Europa and Enceladus can potentially support life, could moons around exoplanets, exomoons, offer similar environments? While no exomoons have been definitively confirmed yet, scientists believe they are likely to exist. Many exoplanets discovered so far are gas giants, much like Jupiter and Saturn, and it's quite reasonable to assume that some of these planets have moons orbiting them. After all, Jupiter and Saturn have between them about a combined 250 moons. These gas giants often orbit their stars at distances too far to be in the habitable zone themselves, but their moons could still be warm enough to support liquid water, thanks to tidal heating. Tidal heating is a key factor that could make exomoons habitable, even if they are located far from their star. just as Jupiter and Saturn's moons experience heating due to the gravitational pull of their parent planets. Exomoons could undergo the same process. This means that an exomoon could have a liquid ocean beneath its surface, even if the exoplanet it orbits is too cold to support life. If these moons have thick ice layers like Europa or Enceladus, they could protect any potential life from the harsh conditions of space, including radiation from their parent stars. In addition to tidal heating, exomoons could benefit from the energy provided by their host planet's magnetic field. Jupiter's strong magnetic field, for example, generates auroras on its moons, producing a source of energy that could potentially support life. On Earth, life relies on energy from the Sun, but on an exomoon orbiting a gas giant, life could tap into the planet's magnetic energy, or the heat generated by tidal forces. Another factor to consider is the atmosphere. If an exomoon has a substantial atmosphere, it could help regulate the moon's temperature and protect it from radiation. An atmosphere rich in gases like carbon dioxide or methane could create a greenhouse effect, trapping heat and keeping the surface warm enough for liquid water. On Earth, the atmosphere plays a crucial role in maintaining temperatures suitable for life, and the same could be true for exomoons. The challenge is detecting these atmospheres from such great distances, but advances in telescope technology will soon allow us to study the atmospheres of distant moons and planets in more detail. Exomoons might also have volcanic activity, which could provide another source of heat and energy. On Earth, volcanic eruptions release gases and minerals that are vital for life. If exomoons experience volcanic activity, it could create environments where life could thrive, especially in combination with water and heat from tidal forces. Volcanic regions on Earth are often home to rich ecosystems, and the same could be true on distant exomoons. The search for exomoons is still in its early stages, but scientists are making progress. One of the most promising techniques is using the transit method to detect the slight dimming of a star's light as an exoplanet passes in front of it. If the planet has a moon, the moon's shadow could also be detected, allowing astronomers to confirm its presence. Detecting these tiny changes in light is extremely challenging, but with more advanced instruments, it's becoming increasingly possible. Exomoons could also be discovered by their gravitational influence on the motion of their host planet. Just as exoplanets cause their stars to wobble due to their gravitational pull, moons can cause slight shifts in the orbit of their planets. By carefully analyzing the movement of exoplanets, scientists might be able to infer the presence of exomoons. The possibility of habitable exomoons expands the scope of the search for life beyond Earth by many orders of magnitudes. After all, there are many more moons than planets in our own solar system. While planets in the habitable zone remain prime candidates, moons around distant gas giants offer another exciting possibility. These moons could one day show us that life can emerge and thrive even in the most unexpected corners of the cosmos. Life in extreme environments. What Earth teaches us. In our quest for the discovery of life beyond Earth, scientists often look to the most extreme environments on our own planet for clues. Life on Earth is incredibly diverse, and some organisms, known as extremophiles, thrive in places that would seem utterly inhospitable. These extremophiles survive in conditions of extreme heat, cold, acidity, radiation, or even complete darkness. Studying them has given scientists valuable insights into the potential for life to exist in the harsh conditions found on other planets or moons. Extremophiles show that life can adapt to environments far more hostile than we previously imagined. One of the most striking examples of extremophiles are the microorganisms that live in hydrothermal vents at the bottom of Earth's oceans. These vents spew superheated water rich in minerals from the Earth's interior. Temperatures near these vents can as high as 464 degrees Celsius or 867 degrees Fahrenheit. Yet bacteria and other simple life forms thrive there. They do this by using chemosynthesis, a process that allows them to convert chemicals like hydrogen sulfide emitted from the vents into energy, This discovery has expanded our view of where life can survive, suggesting that even without sunlight, as long as there is a source of energy, such as the chemical reactions happening around hydrothermal vents, life could persist. This knowledge of extremophiles is particularly intriguing when we consider places like Europa or Enceladus. If there are hydrothermal vents on the ocean floors of these moons, similar to those on Earth, life could potentially exist there. The organisms wouldn't need sunlight. They would rely on chemical energy, just as the extremophiles in Earth's deep oceans do. This idea of life existing in the dark, under extreme pressure and heat, has shifted the way scientists think about where to search for life in our solar system and beyond. Another fascinating group of extremophiles are the thermophiles, organisms that thrive in extremely hot environments. These microbes live in hot springs, volcanic areas, and other places where temperatures can exceed the boiling point of water. In places like Yellowstone National Park, the bright, colorful microbial mats found in hot springs are home to thermophiles that survive in temperatures that would kill most other life forms. These organisms have specialized proteins and enzymes that remain stable and functional at high temperatures. The existence of thermophiles shows that life could survive on planets or moons with high volcanic activity, or in environments heated by tidal forces, much like those found on Io, Jupiter's volcanic moon, which is the most geologically active object in our solar system. On the opposite end of the spectrum, psychrophiles are extremophiles that thrive in extremely cold environments down to 20 degrees Celsius or 4 degrees Fahrenheit, with some extreme cases reported to be as low as -39 degrees Celsius. These organisms are found in the icy waters of the Arctic and Antarctic, where temperatures hover around freezing. They have adapted to these frigid conditions by developing enzymes that can function at low temperatures and cell membranes that remain flexible in the cold. Psychrophiles are of particular interest when considering icy worlds like Europa or Enceladus. If these moons have subsurface oceans, life there would need to endure extremely cold temperatures. The survival of psychrophiles on Earth suggests that similar life forms could exist in these cold, distant environments, as long as there is liquid water and some source of energy. Acidophiles, another type of extremophile, thrive in highly acidic environments. These organisms can live in places with pH levels as low as 1, which would be deadly to most other life. Acidophiles are found in places like sulfuric hot springs or areas contaminated by mining activities. Their ability to survive in such acidic conditions shows that life can adapt to environments with extreme chemical compositions. Life could thus potentially exist on planets or moons with acidic atmospheres or surfaces, such as Venus, which has a thick, sulfuric, acid-rich atmosphere. While Venus itself may be too hostile for life as we know it, the existence of acidophiles on Earth shows that life might still find a way to survive in similarly extreme chemical environments elsewhere in the universe. Another group of extremophiles, called halophiles, thrive in environments with extremely high salt concentrations. These organisms can be found in places like salt flats, salt mines, and hypersaline lakes, where the salt content is far higher than in normal seawater. Halophiles have adapted to these conditions by developing ways to balance their internal salt concentrations with that of their environment. This ability to survive in high salt environments could be useful for life on planets or moons with salty oceans or surfaces. For example, Mars has large deposits of salts on its surface, and scientists have detected traces of salty water flowing on the planet's surface during certain times of the year. The existence of halophiles could indicate that if there is liquid water on Mars, even if it is briny, life could potentially exist there. One extreme condition that life on Earth has managed to overcome is high radiation. Some extremophiles, known as radio-resistant organisms, can survive in environments with incredibly high levels of radiation. One of the most famous examples is the bacterium Deinococcus radiodurans, which can withstand radiation doses thousands of times higher than would kill a human. While 5 grays of radiation are fatal to humans, this hardy bacteria can survive a dose of 5,000 grays without breaking a sweat. It achieves this by repairing its DNA more efficiently than most other organisms. And it isn't even the most extreme example we've discovered. That record goes to Thermococcus gametolerans, which can survive a whopping 30,000 gray. This resilience to radiation is particularly relevant when considering planets or moons that are exposed to high levels of radiation, either from their parent star or from the surrounding space. For example, Europa is constantly bombarded by intense radiation from Jupiter's magnetic field. All of these extremophiles challenge our understanding of life by thriving in environments that life seemingly has no business in. Some hardy organisms have even shown the ability to thrive with little or no oxygen. Anaerobic organisms live in places like deep-sea sediments or the mud at the bottom of lakes where oxygen is scarce. They obtain energy through processes that do not require oxygen, such as using chemicals like sulfur or methane. This further expands the range of places where scientists might find life, as oxygen-rich atmospheres, like Earth's, may not be a necessary condition for life to thrive. These discoveries of life in Earth's extreme environments have profound implications for the search for extraterrestrial life. They show that life is incredibly adaptable and can survive in conditions once thought impossible. Planets or moons that might have been dismissed as too extreme could still be viable homes for life to thrive. As our understanding of extremophiles grows, so does our ability to imagine the kinds of life that might exist elsewhere in the universe. The Great Filter, a grim answer to the Fermi paradox. But despite all of these examples of life thriving in extreme conditions on Earth, the universe remains seemingly lifeless to our eyes. The search for extraterrestrial life has long been guided by a hope that, somewhere in the vast expanse of the universe, intelligent civilizations are flourishing. And yet everywhere we look, it is hard to see any signs that they exist. This discrepancy between what should be and what we see has fueled the Fermi paradox, which asks why, given the vast number of stars and potentially habitable planets, we have not yet encountered any signs of intelligent extraterrestrial life. The Great Filter is one theory that offers a sobering answer to this paradox, suggesting that the rarity of advanced civilizations could be due to existential threats that prevent them from reaching the stage of interstellar travel. The Great Filter theory, as the name suggests, proposes that there is a critical barrier or filter in the development of advanced civilizations that is extremely difficult to surpass. This filter could be any one of a number of potential challenges or catastrophic events that civilizations face, and it may occur at various stages of a civilization's development. If the Great Filter lies behind us, then humanity has already overcome a major hurdle, and advanced civilizations are rare because few species make it through. Conversely, if the Great Filter is still ahead of us, it suggests that future challenges may prevent us from becoming an interstellar civilization, and that we are not as close to reaching this stage as we might hope. Many things need to go right for a spacefaring civilization to emerge from an initially lifeless planet. Any one of those steps could be the filter that is exceptionally hard to cross, or perhaps many of them combine to form the filter. One potential stage where the Great Filter might occur is at the emergence of life itself. The transition from simple single-celled organisms to complex multicellular life could be exceedingly rare. While life may have started on Earth relatively easily, the process of evolving complex organisms capable of advanced thought and technology might be exceptionally rare. This idea suggests that while microbial life might be widespread in the universe, the leap to intelligent life is a rare event, making advanced civilizations less common than we might expect. Or perhaps the key component is the development of technological civilizations capable of space exploration. Even if intelligent life evolves, the transition to a society that can harness energy, build sophisticated technology, and achieve space travel might be fraught with difficulties. Civilizations may face internal threats such as war, environmental destruction, or political instability that could hinder their technological progress. For instance, advanced societies might develop technologies that have the potential for self-destruction, such as nuclear weapons or biotechnology. The inability to manage these technologies responsibly could lead to catastrophic events that prevent a civilization from advancing further. Or perhaps they could find themselves on a planet with such high gravity that rocket engines are simply unfeasible and their civilization remains rooted to their home planet. If self-destruction truly is a filter, then the existence of nuclear weapons on Earth serves as a reminder of the dangers that advanced technology can pose. The Cold War era, with its high tensions and nuclear arms race, demonstrated how technological advancements in weaponry could lead to global existential threats. The fear of a potential nuclear war or environmental collapse highlights the challenge that civilizations face in managing their technological capabilities responsibly. As civilizations industrialize and expand, they can significantly impact their home planet's climate and ecosystems. The concept of climate change, driven by human activities such as fossil fuel burning and deforestation, poses a significant threat to the sustainability of our environment. If other advanced civilizations have faced similar threats, it could explain why we have not yet detected their presence. They might have self-destructed before achieving interstellar travel. Additionally, the Great Filter could involve existential threats that are not yet fully understood. For example, the development of artificial intelligence presents both opportunities and risks. Advanced AI systems could potentially surpass human intelligence and become uncontrollable, posing a significant threat to the continued existence of a civilization. The alignment of AI with human values and ensuring its safety are critical issues that need to be addressed. If other civilizations have grappled with similar challenges and failed to manage them effectively, it could explain the absence of detectable extraterrestrial life. One of the most unsettling aspects of the Great Filter theory is the possibility that it lies ahead of us. If the Great Filter is still in our future, it implies that the challenges we face in advancing to an interstellar civilization are even greater than we currently anticipate. The idea of an impending Great Filter suggests that humanity might be on a trajectory toward potential self-destruction or collapse. This realization could serve as a call to action, urging us to address the existential risks and work towards creating a more sustainable and resilient society. If advanced civilizations are exceedingly rare due to the Great Filter, it implies that we are part of a very select group of species that have managed to reach a certain level of technological advancement. This could be both a humbling and motivating realization. It emphasizes the importance of preserving our civilization and advancing our technological capabilities while avoiding the pitfalls that might lead to our downfall. By exploring this theory deeply, researchers examine both the past and future of civilizations to understand potential risks and challenges. They investigate the history of life on Earth, studying how life evolved from simple microorganisms to complex organisms. They also analyze the potential existential threats that could arise as civilizations develop advanced technologies and face global challenges. They look to other star systems and exoplanets to understand the likelihood of encountering intelligent life. If we find evidence of microbial life on other planets or moons, it might suggest that the early stages of life are relatively common, but that the transition to advanced civilizations is rare. Conversely, if we do not find evidence of advanced civilizations despite numerous searches, it might suggest that the Great Filter is a significant obstacle that prevents civilizations from reaching the stage of interstellar travel. This idea of the Great Filter underscores the need for continued research and exploration in our quest to understand life beyond Earth. The more we learn, the better we are able to estimate and set boundaries on the potential existence of extraterrestrial life. Are we alone? The Drake equation. One of the most famous and influential models designed to tackle the idea of how common life could be is the Drake equation. Formulated by astrophysicist and astrobiologist Frank Drake in 1961, this equation attempts to estimate the number of active, communicative extraterrestrial civilizations in our galaxy. The Drake equation is not a single formula with a definitive answer, but rather a framework that incorporates several factors to provide a range of estimates. It was designed to guide scientific discussion and research by breaking down the question of extraterrestrial life into more manageable components. The equation itself is expressed as n equals r star multiplied by f sub p multiplied by n sub e multiplied by f sub l multiplied by f sub I multiplied by f sub c multiplied by L. In this relatively simple equation, each term represents a factor that contributes to the potential number of extraterrestrial civilizations. First of, there is R. This is meant to represent the average rate of star formation in our galaxy. The number of stars formed per year is a fundamental factor because new stars provide the potential for new planetary systems where life could emerge. Estimates of this factor vary, but current understanding suggests that our galaxy forms about 1 to 3 new stars per year. Next is F sub p. The fraction of those stars that have planetary systems is represented by this term. Not every star will have planets, but advances in astronomy have shown that planetary systems are quite common. Observations from missions like Kepler have revealed that most stars likely have at least one planet orbiting them, leading to estimates that F sub p is quite high, often close to 1. The next part of the equation is n sub e. This denotes the average number of planets that could potentially support life for each star that has planets. Not all planets will be in the right conditions to support life, so this number focuses on planets within the habitable zone where liquid water could exist. Estimates for n sub e can go up or down based on new discoveries, but it is thought that a significant fraction of planets in the habitable zone of their stars could theoretically support life. After that comes F sub L. This is the fraction of those planets where life actually develops. While we know life exists on Earth, we do not yet know how common or rare it is for life to form elsewhere. This factor is speculative, as it depends on whether life is a common outcome or a rare event. Some scientists are optimistic that life is common given the right conditions, while others believe it might be quite rare. Scientists can plug in various numbers that they consider reasonable into this term to generate different estimations. As our knowledge base broadens, numbers that seemed reasonable in the past can be further adjusted, up or down. Then comes F sub 1. This represents the fraction of planets where life evolves the trait of intelligence and goes on to form civilizations. Intelligence is a further level of complexity beyond simple life forms, and its development is not yet well understood. This is another speculative term, as the fraction of planets where intelligence evolves is uncertain and might be small, and intelligence could be an uncommon and unnecessary trait in the evolution of life. Second to last is F sub c. This is the fraction of civilizations that develop technology that allows them to communicate across interstellar distances. It focuses on the ability of a civilization to produce signals, such as radio waves, that can be detected by others. While many civilizations might have the potential for communication, not all will necessarily develop or use these technologies. Finally, L represents the length of time such civilizations can communicate. This factor considers how long a civilization remains technologically active and capable of sending signals before it potentially collapses or ceases to exist. The longevity of a civilization depends on factors like its ability to sustain itself, manage resources, and avoid self-destruction. It may also be the case that these civilizations could develop forms of technologies that we have no current ways to detect. Perhaps there is only a small period of time where advanced alien civilizations put out detectable radio signals out into the universe before switching to tech that does not emit such signals. The Drake equation provides a structured way to think about the factors influencing the existence of extraterrestrial civilizations. By estimating each factor, scientists can generate a range of possible answers. However, many of these factors involve a great deal of uncertainty. For instance, while we have some data on star formation rates and the prevalence of planets, much less is known about the likelihood of life developing, the emergence of intelligence, or the longevity of technologically advanced civilizations. The equation has been instrumental in driving scientific research and guiding observational efforts. For example, the search for exoplanets and the study of their atmospheres help refine our estimates for factors like FP and NA. Efforts to detect extraterrestrial signals, such as those conducted by the Search for Extraterrestrial Intelligence or SETI, focus on FC and L. As technology advances and more data becomes available, our estimates for these factors become more refined. Despite all of its limitations, the Drake equation has had a profound impact on the field of astrobiology and the search for extraterrestrial life. It has inspired numerous scientific endeavors and fostered discussions about the nature of life in the universe. While the equation itself may not provide a definitive answer to whether we are alone, it encourages a systematic approach to exploring the factors that could lead to the discovery of extraterrestrial civilizations. It also highlights the importance of interdisciplinary research. Understanding the potential for extraterrestrial life involves expertise in fields such as astronomy, biology, chemistry, and physics. Each discipline contributes to refining the factors in the equation and expanding our knowledge about the conditions necessary for life. Technosignatures and biosignatures, detecting alien civilizations. The interdisciplinary nature of extraterrestrial life research is obvious when we think about the ways by which we could potentially detect life. There are two major types of signals: technosignatures and biosignatures. Technosignatures are signs of advanced technology, while biosignatures are markers of biological processes. Both types of signals provide different avenues for discovering whether life exists beyond our planet. Technosignatures are signals or artifacts that would indicate the presence of advanced technology, much like the technology we use on Earth. One of the most heavily researched types of technosignatures are radio signals. The idea behind this approach is that advanced civilizations might use radio waves to communicate across space, just as we use radio for communication on Earth. The search for such signals is conducted by projects like the Search for Extraterrestrial Intelligence, aka SETI. SETI researchers use large radio telescopes to scan the sky for unusual or artificial signals that could suggest the presence of extraterrestrial technology. Detecting radio signals as a technosignature relies on the assumption that alien civilizations would use similar methods of communication to those we use. However, it is also possible that advanced civilizations could use different types of technology. For this reason, scientists are also exploring other potential technosignatures, such as laser signals. High-powered lasers could be used by an advanced civilization to transmit information across interstellar distances. Laser signals, being highly directional, would be more difficult to detect, but could be a powerful means of communication. The detection of megastructures such as Dyson spheres or Dyson swarms would be an extremely exciting technosignature. A Dyson sphere is a hypothetical structure that an advanced civilization might build around a star to capture its energy. Think of a ball around the sun where the inner surface of the ball would be covered by solar panels. Such an extraordinary engineering feat would result in a significant change in the star's observed brightness and spectrum. Detecting such a structure would require careful observations of stars to identify any unusual patterns in their light output. Although no Dyson spheres have been detected, the search continues, as finding such structures would provide strong evidence of advanced technology. Tabby's star, a pair of binary stars in the constellation, Cygnus demonstrated unusual behavior in 2015, where its light could dim by as much as 22%. There was quite a bit of excitement as people wondered if this fluctuation was caused by an alien megastructure, while the cause behind Tabby's star's unusual behavior is still not fully explained. The Dyson swarm hypothesis, at least in this case, seems unfortunately unlikely. Beyond searching for specific techno-signatures, scientists are also exploring the possibility of detecting artifacts or changes in the environment that could indicate the presence of advanced civilizations. For example, the presence of unusual atmospheric gases or pollutants could suggest industrial activity. An advanced civilization might produce gases or chemicals that do not occur naturally or that are present in unexpected quantities. Observing the atmospheres of exoplanets for such anomalies could provide clues to the existence of technological civilizations. While technosignatures focus on detecting advanced technology, biosignatures are aimed at finding evidence of life itself, whether simple or complex. Biosignatures are indicators of biological processes that might be present in the atmosphere, surface, or even subsurface of a planet or moon. The most straightforward biosignatures are gases produced by biological activity. For example, on Earth, the presence of oxygen and methane in the atmosphere is a result of biological processes. Oxygen is produced by photosynthetic organisms, while methane is a byproduct of various biological activities. When scientists search for biosignatures on other planets or moons, they look for similar gases or chemical patterns. On planets with atmospheres, telescopes can analyze the light that passes through the atmosphere to identify the presence of different gases. If a planet's atmosphere contains gases that are typically associated with life, such as oxygen or methane, it might suggest the presence of biological activity. If we keep ourselves restricted to planets or moons in our solar system, then surface biosignatures are another area of interest. These include organic molecules or compounds that are produced by life forms. For example, complex organic molecules known as prebiotic molecules could be present on a planet's surface or in its soil. These molecules are building blocks of life and could indicate that a planet has the right conditions for life to develop. Signs of life could also exist in the subsurface. On icy moons like Europa and Enceladus, we know that liquid water exists beneath the surface. If these moons have subsurface oceans, they could potentially harbor life. To detect biosignatures in these environments, scientists are developing methods to analyze samples from the ice, or to send spacecraft with instruments capable of detecting organic molecules or other indicators of life. The search for biosignatures also involves studying extreme environments on Earth, as mentioned earlier. Extremophiles that thrive in harsh conditions help scientists understand what types of biosignatures might be expected in similar environments on other planets. By learning to detect signs of life in extreme conditions on Earth, scientists can better identify potential biosignatures on worlds with similar environments. Detecting these signs is hardly straightforward, as both technosignatures and biosignatures have their own unique challenges. Detecting technosignatures requires distinguishing between natural and artificial signals, which can be difficult given the vast amount of cosmic noise and interference. For example, a signal might be mistaken for a natural phenomenon or for interference from Earth-based sources. Similarly, the search for biosignatures involves interpreting complex data and distinguishing between biological and non-biological processes. Despite the difficulty, the search for both technosignatures and biosignatures remains an active and promising area of research. Technological advances continue to improve our ability to detect faint signals and analyze distant worlds. The development of more sensitive instruments, such as advanced telescopes and space missions, enhances our capacity to explore and understand the universe. SETI, the search for extraterrestrial intelligence. Organizations like the SETI Institute are at the forefront of these ambitious endeavors. SETI is a collective term for a variety of programs and projects dedicated to detecting signals from advanced civilizations beyond Earth. Since its inception, SETI has employed a range of methods and technologies to scan the cosmos for evidence of intelligent life. And its efforts continue to evolve as new advancements in technology and scientific understanding emerge. The roots of modern SETI experiments can be traced back to the 1960s, when the field began to take shape as a serious scientific pursuit. One of the earliest and most famous SETI projects was led by Frank Drake, the same scientist who developed the Drake equation. In 1960, Drake conducted the first modern SETI experiment, known as Project Ozma, using a radio telescope to search for signals from nearby stars. Although the search did not yield any conclusive results, it marked the beginning of a systematic approach to listening for extraterrestrial communications. SETI research primarily focuses on the detection of radio signals, which are thought to be one of the most effective means of long-distance communication. Radio waves travel across space at the speed of light and can cover vast distances without significant loss of signal strength. The basic idea is that advanced civilizations might use radio waves to send messages across the galaxy, much like we use radio waves for communication on Earth. One of the key challenges in SETI is distinguishing between potential extraterrestrial signals and natural cosmic noise. Space is filled with various types of radiation and interference from natural sources such as pulsars, quasars, and cosmic background radiation. Separating genuine signals from this background noise requires sophisticated techniques and highly sensitive equipment. SETI researchers use large radio telescopes to scan the sky and analyze the data for unusual patterns or signals that might suggest an artificial origin. Predominantly, these search efforts are typically divided into two main approaches: targeted searches and all-sky surveys. Targeted searches focus on specific stars or regions of space that are considered more likely to host habitable planets or advanced civilizations. By concentrating on these areas, researchers aim to increase the chances of detecting a signal from a civilization that might be actively transmitting. All-sky surveys, on the other hand, involve scanning the entire sky for signals, regardless of their origin. These surveys aim to detect any potential signals from across the galaxy, even if their source is unknown. One of the most ambitious all-sky surveys was the SETI Institute's SERENDIP, Search for Extraterrestrial Radio Emissions from Nearby Developed Intelligent Populations project, which has been continuously scanning the skies for over 3 decades. Of course, the search for extraterrestrial intelligence is not limited to radio waves alone. Scientists also explore other potential techno-signatures, such as optical signals. The idea behind that is that advanced civilizations might use powerful lasers to communicate across space. Optical SETI projects aim to detect brief bursts of laser light that could indicate the presence of an intelligent civilization. These searches are more challenging due to the narrowness and briefness of laser signals, but they represent an important complement to radio-based efforts. SETI's approach has also evolved with technological advancements. The advent of high-speed computing and advanced data analysis techniques has significantly enhanced the ability to process and interpret large volumes of data. For instance, modern SETI projects use sophisticated algorithms and machine learning techniques to analyze signals and identify potential candidates for further investigation. These tools help researchers sift through the enormous amount of data collected by radio telescopes and identify signals that might be worth closer examination. Further advancements in AI accelerating the search for extraterrestrial life is a topic of growing interest. AI would have a broad potential to revolutionize how we search for alien signals by providing new methods for analyzing data, recognizing patterns, and improving signal detection. One of the key benefits of AI in SETI research is its ability to handle vast amounts of data. Modern radio telescopes generate ginormous quantities of data during observations, and analyzing this data can be a time-consuming and complex task, even with modern computer hardware and software. Machine learning models can be trained to detect patterns and anomalies in the data that might indicate an artificial signal. These models can learn from existing data and improve their accuracy over time, potentially increasing the chances of identifying meaningful signals by orders of magnitude. These ML models can also assist in filtering out noise and interference from natural sources. By training them to recognize the characteristics of cosmic noise, researchers can more effectively distinguish between genuine signals and background radiation. This capability could help reduce the number of false positives and enhance the reliability of SETI observations. Furthermore, AI can aid in the development of new search strategies and techniques. By analyzing historical data and identifying trends or correlations, AI algorithms can suggest new targets or regions of space to explore. For example, AI could help identify stars with unusual characteristics that might indicate the presence of advanced civilizations, or detect patterns in the distribution of techno-signatures that could provide clues about the nature of extraterrestrial life. They can help prioritize targets based on their likelihood of hosting habitable planets or the potential for detecting signals. This approach can optimize the allocation of resources and improve the efficiency of search efforts. While AI offers promising possibilities, it is important to approach its integration into SETI with caution. The development of AI models requires careful consideration of their limitations and potential biases. Ensuring that these algorithms are trained on diverse and representative datasets to avoid skewed results is absolutely essential. SETI's efforts have not only advanced our search for extraterrestrial life, but have also inspired public interest and curiosity. The possibility of discovering signals from distant civilizations captures the imagination and drives us to explore the unknown. But this can also bias us towards the most exciting explanation behind every observation. It is imperative that false signals do not muddy the water and cause us to miss the diamond signal in the rough among all the noise. The wow signal and other mysterious radio signals. One of these tantalizing diamond signals could be the famous wow signal, which stands out as one of the most famous and enigmatic mystery in the history of radio astronomy. Discovered in 1977 on August 15th by Dr. Jerry R. Amon, a volunteer for the Ohio State University's SETI project, the wow signal remains a subject of fascination and debate within the scientific community. The signal was recorded using Ohio State's Big Ear radio telescope, which was scanning the sky for signs of extraterrestrial communications. The signal appeared as a strong and narrow-band radio wave, lasting for 72 seconds, and was notably much stronger than the background noise. Amon, upon reviewing the data, was so impressed by the signal's unusual characteristics that he wrote "wow" in red ink in the margin of the data printout. This simple annotation gave the signal its iconic name. The wow signal was remarkable for several reasons. Its narrow bandwidth and intensity suggested that it was not a natural cosmic phenomenon, but rather an artificial signal. It was also unusual for its duration, as most radio signals from space tend to be either continuous or intermittent, rather than lasting precisely for a short period. Despite numerous follow-up observations and attempts to detect a repeat of the signal, no similar signal has been detected since. The source of the wow signal remains unknown, and its exact nature continues to be debated. Various theories have been proposed to explain the wow signal. Some have suggested that it might have been the result of a transmission from a passing satellite or a spacecraft, though this is considered unlikely given the signal's unique properties. Others have speculated that it could have been a terrestrial signal reflected off space debris or some other Earth-based interference, but no definitive evidence supports this. The possibility that it was an extraterrestrial signal remains an exciting but unresolved hypothesis. The wow signal is not the only unexplained radio signal that has captured the attention of researchers. Over the years, several other mysterious signals have been observed, adding to the intrigue and speculation about alien life. One notable example is the FRB 121102, a fast radio burst, FRB, detected in 2012. Fast radio bursts are intense, brief bursts of radio waves that last only milliseconds, but emit as much energy over that short amount of time as the sun does over 3 whole days. The process that creates FRBs is still not understood, but they have been observed from distant galaxies. FRBs usually come in two forms, non-repeaters and repeaters. The non-repeater are one-off signals, while repeaters manifest in the form of unpredictable, sporadic, and irregular radiation bursts. That was though to be the case until a seemingly third type of FRB was detected in 2018. The signal from FRB 180916 was notable because it repeated at a regular cadence every 16.35 days. This made it the first known periodic repeater. The existence of FRBs has led to various theories, including the possibility that they are caused by rotating neutron stars or a magnetar, which are highly magnetized and rapidly rotating remnants of supernovae. Some, however, have speculated about more exotic explanations, including the idea of advanced technology, though there is no direct evidence to support this. The diversity of mysterious signals like the WOW signal and FRBs highlights the complexity of the search for extraterrestrial intelligence and the challenges involved. Each unexplained signal represents a puzzle that scientists work diligently to solve, and while some are eventually explained by natural or man-made phenomena, others remain shrouded in mystery. The search for extraterrestrial intelligence involves not only detecting signals, but also deciphering their origins and meanings. Whether these signals are the result of advanced technology or natural cosmic processes, they offer valuable insights into the nature of the universe and the potential for life beyond Earth. The mystery surrounding signals like the WOW signal also illustrates the limitations and uncertainties of our current observational capabilities. As technology advances, scientists hope to improve their ability to detect and analyze faint or fleeting signals. Advances in radio astronomy, data processing, and signal analysis techniques may provide new tools for unraveling these mysteries and potentially discovering evidence of extraterrestrial civilizations. But what if the reason extraterrestrial life has proven so elusive was because of something else entirely? Life on rogue planets. Could life exist without a star? When we think about life in the universe, we often picture planets like Earth, orbiting around a star that provides warmth and light. But what if life didn't need a star at all? What if it could survive in the cold, dark reaches of space, on planets that have no sun to call home? Rogue planets, also known as free-floating planets, are planets that have been ejected from their star systems due to gravitational interactions or collisions. Or perhaps they never had a star to orbit in the first place. These planets travel through space, untethered to the gravitational pull of any sun. At first glance, this might seem like a death sentence for any potential life. After all, without the heat and light from a star, how could life survive? Yet, as we explore the extremes where life thrives on Earth, perhaps the challenges are not insurmountable after all. One of the key challenges for life on a rogue planet would be the lack of warmth from a nearby star. However, there are other sources of energy that could keep a planet warm enough for life to exist. One of the most promising ideas comes from the heat generated inside the planet itself. Even on Earth, a significant amount of heat comes from its interior. Deep beneath the surface, radioactive decay generates heat in the planet's core. This geothermal energy powers phenomena like volcanic activity and hydrothermal vents in the ocean floor. These deep sea vents, despite being far from sunlight, support vibrant ecosystems. Microbes around the vents derive their energy not from the sun, but from the chemical reactions caused by the heat and minerals released from the Earth's crust. If a rogue planet had a similar geothermal process, it could create pockets of warmth beneath its surface, where life might thrive. Even without sunlight, simple organisms could survive near these heat sources, feeding off the energy provided by the planet itself. Over time, such life forms could adapt to the darkness and cold of space, just as some life on Earth has adapted to extreme environments. Another intriguing possibility involves the presence of subsurface oceans on rogue planets. Europa and Enceladus, despite being far from the Sun, are kept warm by gravitational interactions with their host planets, which cause their interiors to flex and generate heat, allowing for a vast liquid ocean underneath the surface. On a rogue planet, the heat generated by the planet's core could be enough to maintain liquid water beneath a thick ice shell. If these subsurface oceans exist, they could provide a stable environment for life. Deep beneath the ice, organisms could live in darkness, sustained by the warmth of the planet's interior and perhaps by chemical energy, just like life near hydrothermal vents on Earth. The idea of a hidden ocean on a rogue planet is compelling because it suggests that life could exist even in places where we wouldn't expect it. On Earth, water is essential for life, and if a rogue planet can maintain liquid water beneath its surface, it could support microbial life, or even more complex organisms. For life to survive without sunlight, it would need to find an alternative energy source. On Earth, many organisms rely on photosynthesis to convert sunlight into energy. However, in the absence of a star, life on rogue planets would need to turn to other means of generating energy. One possibility is that life could harness energy from chemical reactions. On Earth, some microorganisms use chemosynthesis instead of photosynthesis. These organisms live in environments where sunlight doesn't reach, like the deep ocean or underground caves. They obtain energy by breaking down chemicals such as hydrogen sulfide or methane, which are released from the Earth's interior. If a rogue planet had a supply of these chemicals, life could potentially use chemosynthesis to survive. This process doesn't require sunlight, only a source of chemical energy. In this way, organisms could thrive deep underground or near hydrothermal vents, where chemical reactions release the energy needed to sustain life. There's another potential energy source that could keep rogue planets warm: tidal heating. Tidal heating occurs when the gravitational forces of nearby objects stretch and compress a planet or moon, generating heat through friction. This process is seen in some moons in our solar system, such as Jupiter's moon Io, which has volcanic activity driven by the tidal forces from Jupiter's immense gravity. For a rogue planet, tidal heating would require interaction with other massive objects. While this might seem unlikely for a planet drifting through space, it's not impossible. A rogue planet could have its own moon, and the gravitational pull between the two could generate enough tidal forces to produce heat. Even without a star, this internal heating could create the conditions necessary for life to exist. In fact, tidal heating could be more effective than geothermal energy alone. If a rogue planet has a large moon or multiple moons, the constant stretching and pulling from their gravitational forces could create enough heat to keep the planet warm for billions of years, long after it has drifted away from its star. It's also worth considering that life on a rogue planet might not be confined to the surface or underground. In some cases, a planet's atmosphere could provide the right conditions for life. On Earth, we've discovered microbes that live high in the atmosphere, where they float on air currents and feed off tiny particles or chemicals in the air. A rogue planet might have a thick atmosphere rich in gases like hydrogen or methane. If life could survive in the planet's upper atmosphere, it might be able to draw energy from chemical reactions occurring in the air. This type of life would be very different from anything we're familiar with, but it's not beyond the realm of possibility. Some have proposed that Jupiter could be a place where life might exist in the upper atmosphere, where temperatures and pressures are less extreme than deeper in the planet. If rogue planets have similar atmospheres, they could support life that floats freely in the air, drifting through the sky on currents of gas. One of the most remarkable things about life on Earth is its adaptability. Life has been found in places once thought to be uninhabitable, deep beneath the ocean, in the frozen tundra, and even in the dry valleys of Antarctica, where almost no water exists. Extremophiles have evolved to survive in conditions that would kill most other forms of life. These discoveries suggest that life is incredibly resilient and can adapt to survive in a wide range of environments. If life can flourish in such extreme conditions on Earth, it's possible that it could also find a way to survive on a rogue planet. Over time, organisms could evolve to make the most of the limited energy sources available, whether from geothermal heat, chemical reactions, or tidal forces. When we think about life, we often imagine it in forms similar to what we see on Earth. But life on a rogue planet might look very different from anything we've encountered. Without sunlight or the predictable cycles of day and night, life on these planets could evolve in ways we can barely imagine. For instance, organisms on rogue planets might not rely on vision at all, since there would be no light to see by. Instead, they could develop other ways of sensing their environment, such as detecting chemical changes or heat. Their metabolisms might be incredibly slow, allowing them to survive with very little energy for long periods of time. If life can survive on rogue planets, it could be living proof that the conditions we consider essential for life — sunlight, a stable climate, a predictable orbit — are not as necessary as we thought. Life, it seems, finds a way, even in the most unexpected places. What if the universe was teeming with life? Imagine a universe teeming with life, where every corner of the cosmos holds the possibility of living organisms, both familiar and alien. What if life, in its many forms, exists across the stars, thriving in environments we have yet to explore? It is certainly a tantalizing thought. One theory that supports the idea of a universe full of life is the panspermia hypothesis. Panspermia suggests that life didn't necessarily originate on Earth, but was instead spread across the cosmos, carried by meteors, comets, or even dust particles. If life can survive the harsh conditions of space, something some microorganisms such as tardigrades on Earth have shown an ability to do, then it's conceivable that the building blocks of life, or even simple life forms, could have hitched a ride on debris ejected from one planet and landed on another. This idea widens the scope of where life might exist. Under panspermia, life could have originated on a planet millions of light years away and traveled across the universe, seeding countless worlds along the way. The conditions necessary for life, it turns out, may not be as unique as once thought. If panspermia is real, it increases the likelihood that life might have taken hold on multiple planets, each evolving in its own unique way. If life is so resilient, able to traverse the universe and establish itself in a wide array of environments, it might not be limited to planets like Earth. Oceans beneath the icy crusts of moons like Europa and Enceladus could harbor living organisms. Even the clouds of Venus, despite their acidic makeup, might hold microorganisms. The universe could be full of life, surviving in forms we haven't yet considered. If the universe is brimming with life, our first contact might not be with advanced alien civilizations, as often depicted in movies and novels. Instead, it's far more likely that we'll first encounter microbial or primitive organisms. This is because life on Earth spent most of its history in simple single-celled forms. For billions of years, microorganisms were the dominant life forms on this planet. Complex life only emerged relatively recently in Earth's history. It stands to reason that if we find life elsewhere, it's more likely to be in the form of bacteria, archaea, or some other primitive organism. Microbial life may not be as glamorous as meeting an intelligent extraterrestrial species, but it would still be an incredible discovery. Finding even the simplest life form elsewhere in the universe would definitely answer one of humanity's biggest questions. Are we alone? It would also suggest that life is not a rare occurrence, but something that happens wherever conditions allow. While microbial life might be more common, what if there are advanced civilizations out there, and they're simply avoiding us? This brings us to the zoo hypothesis, a theory that suggests advanced alien species could be aware of our existence, but have chosen not to make contact. The zoo hypothesis draws on the idea that more advanced civilizations might see humanity as a species that is not yet ready for interaction on a cosmic level. Just as humans observe animals in a zoo without directly interfering in their behavior, these alien species could be watching us from afar. They may have their reasons for keeping their distance. Perhaps they're waiting for us to develop further, to reach a level of technological or social maturity before initiating contact. This hypothesis can also be viewed through the lens of ethics. A more advanced civilization may have rules or guidelines about interfering with less developed species. We already practice something similar on Earth, with conservation efforts that aim to preserve endangered species and environments without disturbing them. If aliens are following a similar ethical code, it could explain why we haven't seen any direct signs of their presence. Alternatively, some theorists suggest that these civilizations might not be avoiding us out of respect, but for their own protection. Humanity, in its current state, may be seen as unpredictable or even dangerous. From our history of conflict to our rapid technological advancements, it's possible that aliens see us as too volatile to engage with at this point in time. They may choose to wait and see how we evolve before risking contact. If the universe is full of life, why haven't we found clear evidence of it yet? The answer might be simpler than we think. Our current methods of searching for extraterrestrial life are limited. Most of our efforts, such as scanning for radio signals or studying the atmospheres of distant planets, rely on technology that is far from perfect. We could be missing signals or signs of life simply because we don't know exactly what we're looking for. Another possibility is that alien life exists on a scale or in a form that we can't yet detect. Our search is largely focused on carbon-based life, similar to what we know on Earth. But what if life elsewhere in the universe is based on entirely different chemistry? What if the timescale they operate at is much shorter or much longer than our own, or their communication methods are beyond our understanding? Moreover, the vast distances between stars and galaxies make it difficult to imagine regular interaction between civilizations. Even if there are intelligent beings out there, they could be so far away that communicating with them would take thousands or even millions of years. The speed of light, while incredibly fast, is a limiting factor when it comes to interstellar communication and travel. Ideas like the zoo hypothesis are hardly the only wild ideas that scientists have come up with as they explore the idea of life out there in the universe. With life being as hardy as it is, and the universe teeming with wild objects, there is always room to speculate about the weird and wonderful forms of life that might be out there. Terraforming exoplanets. Can we make other worlds habitable? Of course, finding native life on another celestial body is not the only way for life to propagate throughout the cosmos. What if we were the ones to seed life on other planets and moons? As we look to the stars and dream of exploring distant worlds, the idea of making other planets habitable for humans, terraforming, becomes an intriguing possibility. Terraforming is the process of transforming an alien environment to resemble Earth, making it suitable for life as we know it. It's a concept that has been explored in science fiction for decades, but could it ever become a reality? And even if it's possible, should we attempt it? At the core of terraforming is the idea of creating conditions that support life. This means altering the atmosphere, temperature, and surface of a planet to make it more Earth-like. For humans to survive, we need breathable air, liquid water, and temperatures that aren't too extreme. These are the basic requirements, but they're not easy to achieve on most exoplanets, planets outside our solar system, or even on some of the planets and moons nearby. One of the biggest challenges of terraforming is altering a planet's atmosphere. Most exoplanets don't have the right mix of gases for humans to breathe. Earth's atmosphere is made up of about 78% nitrogen and 21% oxygen, with small amounts of other gases like carbon dioxide. For a planet to be habitable, we'd need to increase the oxygen levels and reduce harmful gases like carbon dioxide, methane, or sulfur compounds. Scientists have proposed several ways to change a planet's atmosphere. On many planets and moons, the atmosphere may be too thin, too thick, or composed of gases that are not conducive to life as we know it. One idea is to introduce plants or microbes that can perform photosynthesis, the process by which plants on Earth turn carbon dioxide into oxygen. If we could spread these organisms across the surface of a planet, they could slowly produce oxygen and create a more breathable atmosphere. However, this process would take a very long time, potentially hundreds or even thousands of years. Terraforming is not a quick solution. It requires patience and long-term planning, as the entire planet's ecosystem would need to be reshaped. Another major hurdle is temperature. Many planets are either too cold or too hot for human life. Mars, for example, is far too cold, with average temperatures of between -78 degrees Celsius or -108 degrees Fahrenheit to 5 degrees Celsius or 41 degrees Fahrenheit. If we want to make a planet like Mars habitable, we would need to warm it up significantly. One proposal is to release greenhouse gases into the atmosphere to trap heat, much like what happens with Earth's own greenhouse effect. By pumping gases like carbon dioxide or methane into the atmosphere, we could artificially raise the planet's temperature. This method has been considered for Mars, where there is already frozen carbon dioxide in the polar ice caps. If we could release this carbon dioxide into the atmosphere, it might start a warming process that could eventually melt water ice, creating liquid water on the surface. Warming up a planet also involves finding a stable source of energy. On Earth, the sun provides most of the energy that warms the planet. On a distant exoplanet, especially one farther from its star, we might need to find other sources of heat. One idea is to use large mirrors or solar reflectors in space to direct more sunlight onto the planet's surface, helping to raise temperatures. Water is, of course, essential for life, and any terraforming effort would need to create or maintain sources of liquid water. On some planets, like Mars, there is water in the form of ice. If we can melt this ice, we could create lakes, rivers, and even oceans. But liquid water can only exist if the planet is warm enough, so this step is closely tied to the challenge of raising the temperature. On exoplanets without natural water sources, we would need to find a way to import or produce water. Some scientists have speculated about the possibility of redirecting comets or asteroids made of ice to crash into the planet's surface. These space objects could release huge amounts of water as they melt. However, this process would be extremely risky and difficult to control. Even if we could create water, we would also need to make sure it stays on the planet. Some planets have weaker gravity or lack a magnetic field, which could allow water to escape into space over time. Ensuring that water remains stable on the surface would require careful consideration of the planet's geological and atmospheric conditions. Terraforming also isn't just about making the planet comfortable for humans, it's about creating a whole ecosystem that can sustain life. This means introducing plants, animals, and microorganisms that can interact with the planet's environment and maintain a balanced system. On Earth, ecosystems are incredibly complex, with countless species playing specific roles in maintaining the flow of energy and nutrients. To terraform an exoplanet, we would need to build something similar from scratch. The first step might involve introducing hardy microbes and plants that can survive in extreme conditions. These early colonizers could begin to alter the soil and atmosphere, laying the groundwork for more complex life forms. Over time, we could introduce animals, though this would be much further down the line once the environment is stable enough to support them. The challenge here is not just scientific, but ethical as well. If we bring life to another planet, we could be disrupting any native ecosystems that might already exist, even if they are as simple as microbial life. There's also the risk that the introduced species could go out of control or cause unintended consequences, much like invasive species on Earth can devastate local ecosystems. Ensuring that we create a balanced, sustainable ecosystem would require careful planning and a deep understanding of the planet's natural processes. Some believe that if a planet has no life, or if the life it has is very simple, terraforming could be justified. In this view, transforming a dead or inhospitable world into one that can support human life would be an extension of humanity's survival instinct. With Earth facing challenges like climate change and overpopulation, finding new worlds to live on might one day be necessary for the survival of our species. Others question if terraforming is the best use of our resources. Instead of focusing on changing entire planets, we could invest in building space habitats, large artificial structures that could house humans in space. These habitats could be designed to provide all the comforts of Earth without the need to transform a whole planet. Building space stations or colonies in orbit around planets or even in deep space might be significantly more practical. Still, the idea of walking on the surface of another world, breathing its air without a spacesuit, is an alluring one. Terraforming, while being a potentially century or millennia-long process, holds the promise of making this dream a reality. As our technology advances, it's possible that we'll develop new ways to make terraforming faster or more efficient. For example, genetically engineered organisms could speed up the terraforming process. But even with advanced technology, there's no guarantee that terraforming will ever be fully successful. Planets like Mars have very different geological and atmospheric conditions compared to Earth, and there's no way to predict exactly how they would respond to terraforming efforts. It's possible that even after centuries of work, a terraformed planet might never be as comfortable or stable as Earth. Even if we successfully terraform a planet, keeping its environment stable over the long term could be difficult. On Earth, natural processes like the carbon cycle and the water cycle help regulate the climate and keep ecosystems in balance. On a terraformed planet, we'd need to create artificial systems to mimic these processes. If something went wrong, if the atmosphere became too thick, or the temperature fluctuated too much, life on the planet could quickly become unsustainable. Terraforming represents both an exciting opportunity and a huge challenge. It's a way of expanding humanity's reach beyond Earth, giving us the chance to create new homes in distant corners of the galaxy. But it's also a reminder of the limits of our knowledge and technology. Whether or not we'll ever be able to transform other worlds into places we can live remains to be seen. But the dream of terraforming continues to push us to explore, innovate, and think deeply about our place in the universe. Are we prepared for the answers we seek? As humanity stands on the precipice of profound discovery, the question of whether we are truly prepared for the implications of finding extraterrestrial life, be it microbial or intelligent, remains an open and pressing issue. The exploration of other worlds, the search for habitable environments, and the quest to understand the potential for life beyond Earth all point to a future where such discoveries may become a reality. Yet this journey into the unknown also inspires reflection on our readiness to handle the profound consequences that such discoveries could bring. The prospect of discovering microbial life on distant planets or moons might seem less daunting compared to the encounter with an advanced extraterrestrial civilization. Nonetheless, the implications of finding even the simplest forms of life would be monumental. It would challenge our understanding of life's origins, its distribution across the universe, and our place within the cosmic tapestry. Discovering that life exists elsewhere would not only validate our theories about the conditions necessary for life, but also highlight the resilience and adaptability of life in the universe. This realization would prompt a re-evaluation of our approach to planetary exploration, environmental stewardship, and the search for more complex forms of life. On the other hand, the discovery of intelligent extraterrestrial civilizations would pose an entirely different set of challenges and questions. Such a finding could revolutionize our understanding of technology, society, and communication. The potential for learning from a more advanced civilization is exhilarating, yet it comes with its own set of risks and uncertainties. The interactions with such civilizations could bring about shifts in global dynamics, ethical considerations, and philosophical reflections on humanity's role in the universe. The potential for miscommunication, cultural clashes, or even existential threats could complicate our response and necessitate careful deliberation. As we move forward in our quest for knowledge, it is essential to reflect on whether humanity is ready to embrace and navigate these profound discoveries. Are we equipped to handle the societal, ethical, and philosophical ramifications of finding life beyond our planet? These questions extend beyond the scientific realm and delve into the heart of what we as humans value. I hope this video helped you reflect on these questions and broadened your mind to the possibilities of what could be out there among the stars. If you enjoyed it, consider leaving a like and subscribing to the channel. Thanks for watching.